Hello viewers, I am Dr. Maninder Singh from Department of Computer Science, Punjabi University, Patiala. Today's lecture is on ciphers. In this lecture, first of all, I will give a brief idea about ciphers, then different types of substitution ciphers will be explained in detail along with their examples. Let us start. Now, what is a cipher? Cipher is an exact mathematical process used in encrypting and decrypting a message, or in other words, a cipher is a way to make a word or message secret by changing or rearranging the letters in the message. There are two basic ways of encrypting a message, either through substitution or through transposition. In substitution, we replace a symbol of plain text with another symbol. For example, university may be encrypted as VOJWFSTJUI. Here, in each letter of a message is substituted or replaced by its next letter in the alphabet. In transposition, we rearrange the order of the symbols of the message. For example, university may be encrypted as UIESTNVRIY. In this case, letters at odd position have been written first. Today, we are going to talk about substitution ciphers only. Some of the common substitution ciphers are shift cipher, affine cipher, Playfair cipher, Hill cipher, and there are two polyalphabetic ciphers, Wigner and one-time pads, and the last cipher is the book cipher. Let us start with the Caesar cipher or shift cipher first. The Caesar cipher is one of the earliest known and simplest ciphers. The Caesar cipher, also known as a shift cipher, is named after Julius Caesar, who is said to have used it to send messages to his journals over 2000 years ago. It is a type of substitution cipher in which each letter in the plain text is shifted a certain number of places down the alphabet. The key is the number of letters you shift. In a Caesar cipher, each letter of plain text is replaced by a letter further along in the alphabet. You can think of it as shifting the alphabet to the left. The key of a Caesar cipher is the number of places the alphabet is shifted. In shift cipher, first we translate all of our letters to numbers, that is A equal to 0, B equal to 1, C equal to 2, and so on, and Z equal to 25. For example, with a shift of 1, A would be replaced by B, B would become C, and so on. With the shift of 2, A becomes C, B would become D, and so on. And with the shift of 3, A would become D, B would become E, C would become F, and so on. And you can see that X becomes A, Y becomes B because of a shift of 3. So, you can use this key to help you when you are trying to encrypt a message. So, this is how encryption works in Caesar cipher or shift cipher. So, we can conclude that to pass an encrypted message from sender to receiver, it is first necessary that both parties have the key for the cipher, so that the sender may encrypt it and the receiver may decrypt it. For Caesar cipher, the key is the number of characters to shift the cipher alphabet. Now, let us see how to decrypt a message with a key size 3. In this case, we swap our alphabets. I put my original alphabets below and my encrypted alphabets above, and then I go from top to bottom. So, when we encounter D, I switch it with an A, and whenever I encounter E, I switch it with B. So, basically I go 3 letters back in the alphabet. So, when I encounter A, I switch it back to X, because back 1 is Z, back 2 is Y, and back 3 is X. So, this is how you decrypt, and it is very important to remember you have got to shift by whatever shift you are using. Suppose someone sent you a message that is encrypted by a shift of 17. You have to shift it by 17 when you decrypt. If you shift it by a different number, your message won't make any sense. So, just keep that in mind. Now, we can represent this encryption system as a pair of algorithms. E subscript x is equal to x plus k mod 26 and D subscript x is equal to x minus k mod 26, where E and D stands for encryption and decryption respectively. What we are going to do here, we are going to assign the numbers 0 to 25 to the letters A to Z respectively. The reason for doing that is when we try to encrypt a message, we do it mathematically using these two equations. So, you can see here I have got E subscript k x, which means encryption of x with the shift of k is equal to x plus k, that is, add the shift to letter, x is the letter in this case. So, add shift to each letter of the message and for each letter mod that by 26. Now, the question here is why we mod that by 26? The answer is we have only 26 letters in English. Say if we have got a letter Z which has a value 25 in this case, and if we have to shift of 7, then 25 add 7 is 32, and 32 is not matched to any letter in a notation. So, what we have to do is we have to mod it by 26 to get a value back to between 0 and 25. So, when you mod something by 26, the result will always remain between 0 and 25. And to decrypt, we have to subtract the shift and then mod that by 26. So, for example, if we have A and the shift was 5, so numerical value of A is 0. So, 0 subtract 5 is negative, and when you mod negative 5 by 26, what you end up with is 21. This is how we represent encryption and decryption algorithms. Just to give you a more concrete example, I will show you encryption in an actual message. So, here is my secret message that I want to send to someone is, this is a secret message and I want to encrypt it with a shift of 15. So, I apply a shift of 15 to each letter of my plain text message, and the result is the ciphertext message, which is IWXH XH P HT RGT I BTHH PVT. Now, there are some big problems associated with the Caesar cipher. Like I said, it is the most basic cipher that exists. So, the problems with Caesar cipher is that it does not provide message integrity, and I will explain what that means if you do not know what it is in a second. And the other issue is it is very easy to break Caesar cipher. So, if I am trying to send a message to my friend and someone somehow manages to see that message, that person would be able to decrypt the ciphertext very easily. So, this type of attack is called man in the middle attack. What happens is sender would try and send his encrypted message to receiver, but the attacker intercepts the message. So, now the message is not going to reach receiver at all unless the attacker sends it on. Before he sends it on, what is he going to do is he is going to apply his own shift and he is going to shift it further by 5. So, he is going to take each letter of ciphertext and shift it further by 5. So, receiver is going to receive the message modified by the attacker. Now, I also said that Caesar cipher is very easy to break and it is breakable by one of the simplest form of the attack, and that is brute force attacks. So, if we can attack or intercept a ciphertext, then we can decrypt it by applying all the different shifts 0 to 25 and determine which of the results is the actual plain text. There are also other methods like frequency analysis to decrypt, but you do not need those methods to decrypt or break Caesar cipher purely because it is so simple to break just by brute forcing it. The next cipher is the affine cipher. As we have already seen, there are some problems associated with the use of Caesar or shift cipher. Now, we try to improve the shift cipher by generalizing the encryption function. If you can recall that the actual encryption of the shift cipher was the addition of the key to the letter. The affine cipher encrypts by multiplying the plain text by one part of the key, followed by addition of another part of the key. The mathematical function used for encryption in the case of affine cipher is Ex is equal to Ax plus B mod 26. With the key KAB, which has the restriction that GCD of A and 26 is equal to 1. In the affine cipher, the letters of an alphabet of size m are first mapped to the integers in the range from 0 to m minus 1. First, we translate all of our letters to numbers, that is A equal to 0, B equal to 1, C equal to 2 and so on, and Z equal to 25. The affine cipher then uses modular arithmetic to transform the integer that each plain text letter corresponds to another integer that corresponds to a ciphertext letter. The encryption function for a single letter is Ex is equal to Ax plus B mod m, where modulus m is the size of the alphabet, which is 26 in case of an English language, and A and B are the key of the cipher. The value A must be chosen in such a way that A and m must be co-prime, that is GCD of A and m has to be 1. B has to be between 0 to m minus 1. We get to choose what our A and B keys are going to be. For the moment, we can take that 3 is co-prime with 26. So, 3 times letter plus B, in this case I can take B as 5, which is in the range 0 to m minus 1, and we modulus it by 26. So, let us take the letter C in this example. We know that the value of C is equal to 2. So, the encryption of the letter C is going to be 3 times 2 plus 5 modulus 26, and the answer is 11. So, we can now check what the number 11 is. In our alphabet system, the number 11 is the letter L. So, the encryption of letter C is L. Now, let us look at the decryption using affine cipher. The decryption function used in affine cipher is d of x is equal to multiplicative inverse of A into x minus b mod m. Here, first of all, we have to know how to find the multiplicative inverse of the number which we need, and there is a very simple way of doing this. As you can remember, the key value A is 3. So, we have to find the multiplicative inverse of 3. There is a very simple formula of doing this, and the formula is I into m plus 1 divided by A. Now, all we have to do here is we have to start substituting in numbers starting from 1 for I, and once we get a value that is a whole number, not decimal point, we know that is going to be our multiplicative inverse. Now, let us try. Suppose the value of I is 2, value of m is 26, and A, as we already know, is 3. So, 2 into 26 plus 1 divided with 3 is 17.33, which is not a whole number. So, 2 does not work here. Now, let us try 3. The value of I is 3, the value of m is 26, and A, as we already know, is 3. So, 3 multiplied with 26 plus 1 and divide with 3 is 26.33, which is not a whole number. So, 3 does not work here. Now, let us try 4 here. The value of I is 4, the value of m is 26, and A is 3. So, 4 into 26 plus 1 divided with 3, and we get 35 as final answer, which is a whole number, that is, it does not contain any fractional part. Now, we have the multiplicative inverse, Now, we go on and do the decryption. The decryption function is d of x is equal to multiplicative inverse of a into x minus b mod m. Let us find out the plain text letter for the ciphertext letter L. As we know, L is equal to 11, and what were the values of a and b during encryption? It is 3 and 5. We have just found the multiplicative inverse of a, which is 35. Now, put all the values in the decryption function, that is d letter L is equal to 35 11 minus 5 mod 26, and we get 2 as the answer. So, we can now check what number 2 is in our alphabet system, and the number 2 is the letter C. So, the decryption of letter L is C. So, this is all about the affine cipher, and the next cipher is the Playfair cipher. The Playfair cipher was the first practical digraph substitution cipher. I will explain the meaning of digraph later on. The scheme was invented in 1854 by Charles Wheatstone, but was named after Lord Playfair, who promoted the use of the cipher. The technique encrypts pairs of letters, which are called digraphs. Instead of encrypting single letters as in the simple substitution cipher, the Playfair is significantly harder to break, since the frequency analysis used for simple substitution ciphers does not work with it. The encryption method in Playfair cipher uses two main processes. The step 1 is creation and population of matrix. The step 2 is encryption process. Now, let us start how to perform the step 1, that is the creation and population of matrix. The first step is to choose a key or a keyword. The only rule while choosing a keyword is that it cannot contain repeating letters. If the keyword or key contain repeating letters, then simply delete those repeating letters. Swimming would become SWIMNG. The second M and second I have been deleted. After you have chosen a keyword, the next step is to create a table using keyword. The Playfair cipher makes use of 5 into 5 matrix, which is used to store a keyword that becomes the key for encryption and decryption. The way this entered into the 5 into 5 matrix is based on some simple rules. The first rule is enter the keyword in the matrix row wise and then top to bottom. The second rule is drop duplicate letters, that is no repeating letters in the matrix. The rule 3 is fill the remaining spaces in the matrix with the rest of the English alphabets that were not part of our keyword. While doing so, combine I and J in the same cell of the table. Now, let us do an example, and in this example our keyword is Playfair example. Then the 5 into 5 matrix or a table containing our keyword will look like as shown in figure. Explanation of this matrix row wise is as follows. Row 1 of this matrix contain the first 5 letters, which is PLAYF of our keyboard, which is Playfair cipher, and does not contain any duplicate alphabets. Now, we move to row 2, and in this case the first 4 letters are just the continuation of keyword IREX, as we have already covered PLAYF in the first row. However, after this we can see a repetition of alphabet A. Therefore, as per rule 2, we have to disregard repeating A and pick the next alphabet, which is M. Let us now evaluate what part of the keyword is covered in the first 2 rows. Our keyword is Playfair example. Our first 2 rows contain PLAYF and IREXM, which means only 3 letters are left, that is PL and E. But PL and E are the duplicates and are already included in the first 2 rows. Therefore, all of our keyword alphabets are covered now. Hence, here now we would consider a rule 3. The rule says that remaining part of the matrix should be covered with alphabets from A to Z. that are not covered so far. According to this rule, we see B, C, D, G and H will fit into the third row of our matrix. In row 4 and 5, we simply apply the rule 3 and contains K, N, O, Q, S and T, U, V, W, X respectively. So, we have created the matrix and step 1 of the encryption process is over, and let us move to step 2. Next step is the encryption process. Let us say we want to send the plain text message, my name is Atul. Now, let us see what is the ciphertext equivalent of this message. The series of steps involved in the encryption are: the first step is to delete the spaces in the message, then the message becomes my name is Atul without any spaces, and next is to separate the letters into digraphs. Digraphs means set of 2 letters, then it becomes MY, NA, ME, IS, AT and UL. Next, we have to keep in mind some rules while encrypting the digraphs. In the first rule, if both alphabets are the same, add an X after the first alphabet. For example, if the digraph contains MM. So, here the alphabets are same. So, instead of writing MM, we should write MX. Now, the next step is if both letters are in the same row, then they are replaced by the letters to the immediate right of each other. If a letter is at the end of a row, F for example, it is replaced by the letter at the beginning of the same row, that is letter L. Next rule is if both letters are in the same column, then they are replaced by the letter immediately beneath each one. If a letter is at the bottom of a column, V for example, it is replaced by the letter at the top of the same column, that is letter A. If the alphabets are not in the same row or column, then draw a box around the digraph letters such that each letter in the digraph are in opposite corners of the box. Replace each letter in the digraph with the letters found in the other corner of the box in the same row. As you can see, X and N are not in the same column or in the same row. For our first step is to draw a box around X and N with X and N in the opposite corners. Then we look at the letters in the same row beyond the other corner of the box. Then X becomes R and N becomes Q. If there is an odd number of letters, end the word with X. Now, we go back to our example. Our keyword is Playfair example and our message is my name is Atul. Now, let us see how encryption happens in Playfair cipher. First, we break the message into pairs of 2 alphabets called digraphs. Then it becomes MY, NA, ME, IS, AT and UL. Now, we apply our algorithm to this message. The first pair of alphabets is MY. Look at the matrix. We see that alphabets M and Y do not occur in the same row or column. Therefore, we need to apply step 4 here. That means replace this text with the text diagonally opposite to it. In this case, text is XF. Next pair of messages ME, apply step 2 here and the cipher text is IX. Next pair of messages IS, apply step 4 here and the cipher text is MK. Next pair of messages AT, apply step 4 here and the cipher text is PV. Next pair of messages UL, apply step 3 here and the cipher text is LR. So, our plain text is my name is Atul and it becomes XF, OL, IX, MK, PV and LR. So, friends, this was about ciphers and only 3 ciphers have been covered so far in this lecture and the remaining will be discussed in the next lecture. Hope all the concepts are clear to you. Hope to see you in the next lecture. Till then, goodbye. Thank you.